In this excursion, we want to introduce hash functions. Hash functions play an important role in many different applications in computer science. So the idea behind such hash functions is that they map large amounts of information, messages, text, videos, into short strings, so-called fingerprints, which are characterizing this long information. Mathematically, there is a function, the hash function, and the hash function maps a message, a long message, into a hash function. When we map long words to small words, then eventually same hash value can occur for different messages, for different long words. So here it's important to have this in mind, that hash functions are non-injective. There are different applications of hash functions also in the field of internet security. With this particularly hash functions, we speak of cryptographic hash functions. But let's start with two applications. The first application is the secure storage of passwords by concealment on provider side. If a user wants to log in into a service, he has to prove and has to identify himself, so he has to give his username and his passwords. What is not okay if, when on the service provider side, the password is directly stored in a database, in the user database. In that case, everyone that has access to the user database can also see the password of the person. So the password is hashed before it's stored in the user database, so that's not easily reproducible. Another application is that from a long document we create fingerprints, for example, to send the long document together with a smaller copy, which helps the user to find out whether the document has arrived in the right way. Here is an example. So, for example, one wants to send the message, I like OpenHPI. Then there's a famous hash function, SHA-256. And then we have our message, and then by means of this hash function, the message is described, the hash value is produced exactly in that length. In this case, it's only an example, we have such a short message and a long hash value in the usual application. Of course, we have huge messages, for example, a document, a contract, or another thing, so that for a case of verification, the hash value is sent together with the document. Let's have a closer look to this password security application of a hash value. To secure the password, the service provider stores the hash value of a password instead of the password itself. When we speak about password security, I mentioned this already, then we have to avoid conflicts in case of users which use the same password. If they use the same password, then also the same hash value would be created, and it's no more distinguishable. So to the password, a salt is appended. Random salt prevents that identical hashes of the same password and makes it more difficult to analyze and to crack passwords. So for example, to users use a password hello, then a salt is added, so it's a random string, and then this password appended with the salt, the hash function is applied. Then we get the hash value, and this hash value, that is stored in the user database of the provider. Of course, the provider needs also to remember the salt, so the hash is stored together with the salt. For this kind of applications, for generally this kind of application of hash functions in security relevant areas, one needs special type of hash functions so-called cryptographic functions. Before I go into more details, let's consider a second example. The second example, which plays a role, for example, in the context of digital signatures. Digital signatures we will discuss in week 5. So here I only give the principle why the hash function play an important role for such security mechanisms. The idea is that in addition to the document itself, a specially encrypted digital copy of the message is sent. And if one would apply the encryption function to the document, to a large document, for example, to a video, then we would get a very large encryption. It would need a lot of processing power. And so the idea is to not encrypt the full document. No, the idea is to apply a hash function to the document and then to encrypt the short hash value. So since this helps to avoid, to increase the performance, to avoid a long and complicated computation, so only a short hash value of the document, the fingerprint, is encrypted and sent together with the document, and so the user, the receiver, can check whether the document has reached himself in a good way. Here is the illustration. We have the document. The document, we apply a hash function. I apply an old-dated hash function in this example because they produce small hash values. Here's the hash function, and then with the private key of the user, this hash value is encrypted. Send it together with the document, and then the receiver can check, can use the public key of the sender, can encrypt the hash value, can compare this hash value with the hash value that is produced by the document, and if both increase, then there is a proof that the document, for example a contract, reached the user in the right way. For both this application of hash functions in the security area, there are some additional requirements for hash functions. And if these requirements are fulfilled, we speak of cryptographic hash functions. The problem with hash functions is they map large amount of information to short information. And so different large documents can have the same hash value. We speak of a collision, because then it's no more a proof whether this fingerprint comes from that document or from another document. So in the case of cryptographic hash functions, it should be very difficult to produce such collisions. And in order to make this difficult to produce such collisions, a requirement for the cryptographic hash function is that they should be uniformly distributed. Another requirement is that even small changes of the input value should result in large changes in the hash value. Assume there is a document, an important contract, and only a small piece is changed, for example the price or the date. Then there is a small change, and if there would, and this small change, if someone tries to manipulate this, can be detected by means of the requirement that cryptographic hash functions have a large difference in the hash value, even for documents which are very similar. So working with such type of hash functions, it's a known sub-area of cryptography, so it's a big research field, and it's very important and has many applications in the security area. Mathematically, the requirements can be formulated in such types of properties that need to be fulfilled. The hash function means collision resistance to message n. If it is practically impossible to construct a different message with the same hash value. So an attacker, it should be very difficult it should be almost impossible for an attacker to produce a faked message with the same hash value. A hash function a cryptographic hash function should be collision resistant, and this means that it is practically impossible to find two different messages with the same hash value. And the cryptographic hash function should be one-way functions. One-way function means that it's practically impossible to reproduce from a hash value Z the value of a message M. So in one direction, compute the hash value of a message, that's easy. But the reverse direction, reconstruct from the hash value the message itself, this should be at least practically impossible. It needs so much computational power, it needs so much time that's useless to apply. So cryptographic, now we can define it correctly, cryptographic hash functions is a collision-resistant hash function. A few words about the length of the hash values. We said we have the long information, the long words, the long messages, which are mapped to small hash values. And of course, for the application, it would be better if the hash value is small. But the hash value needs a certain length to be able to fulfill what he should fulfill. And to see this, let's start with considering the so-called birthday paradox. Birthday paradox says in a group with only 23 randomly selected people, the probability that at least 2 have a birthday on the same day is greater than 50%. We have 365 days a year. So 365 different possibilities for birthday, and only 23, a group of 23 randomly selected persons is enough. That the probability that at least 2 have the same day, have on the same day birthday, is greater than 50%. Mathematically, with this fact, so with this birthday paradox, one can estimate the probability of hash value collisions. And every time this is bad if there's a collision of a hash value, because this provides a possibility for an attacker to do some wrong things. So if we apply this idea and if we apply this fact, the birthday paradox, then we can say that if the hash value would have a length 120 bit, this was in the past the recommended minimum length, then with probability greater than 50%, collision can be found on 2 to the 64 random input values. So it's a huge amount of input value, that's true. But considering the high computational power of modern machines, this is for attackers not practically impossible to misuse this and to create collisions. If we insist on a hash value length of 160 bit, so it is request with DSS, then with a probability of greater than 50%, a collision can be produced a collision can be found on 2 to the 80 random input values. What are the attacks against cryptographic hash functions? Of course, we already mentioned collisions play an important role, so the aim of an attack is to try to create a collision. To create a collision, that means to calculate of 2 different messages, to find 2 different messages with the same hash value. Or to calculate a new message from a predetermined hash value. So the hash value that was used, for example, to secure a password or to secure an information, that the attacker tries to find another password or another message with identical hash value. And we discussed already the birthday attack. So in falsifying messages to generate a pair of messages with the same hash value of length n is possible with 2 to the n half attempts. This is a result, this is a conclusion from the birthday paradox. So this attack is every time possible. And now you see, this n is important. This n needs to be large. It needs to be small to make the application of hash value efficient as possible. But to guarantee security, it needs to be large. So every time it is the art of such hash functions to find the right balance. So with a birthday attack, it's possible in falsifying messages to generate 2 messages with the same hash value of length n, that 2 to the n half attempts are possible. Protection, of course, use long hash values. For example, 512 bits. This is in the length of the SHA-512 hash functions. Why? Then n is equal 512, so you need 2 to the 256 56 attempts to find a collision. There is another attack, the substitution attack, an attack against hash functions. And this works with any cryptographic hash functions. There is no possibility to protect against. The idea is let m be the length of the hash value, of the hash value h of the message m. And then the attacker formulate and change many positions in this hash value. So a fake message is formulated and changed are made to t greater than m positions. For example, spaces are inserted or some which does not change the meaning of the document, but formally change the encryption of the document, so the formulation as a text file, for example. So for all resulting 2 to the t greater, of course, than 2 to the m counterfeits, it is very likely that different hash values are calculated so that one of the counterfeits has exactly the predetermined hash value h of our message the attacker wants to attack. This is a picture principle from combinatorics. It is a huge number to make such a change and modification, but it works. And of course, what you see, protection is this m should be as large as possible to make it very difficult for an attacker to come up with such amount of different versions of the regime. Let's speak and consider some of the popular hash functions. MD5, for example, message digest 5 is a very popular hash function which was released in 1991 by Ron Rivest. It is an improved version of another hash function of MD4. And the problem is these hash functions, MD5 as well as SHA-1, are currently very widely used, but they were released years ago to the standard by the Internet Authority IETF. But similar like SHA-1 with 512 block length and 128-bit hash values, the security is no more. It's no more possible to use it because for today's computers and application, this length of 128 bit length hashes are considered too short. To explain this a little bit more in detail, the message is put into blocks. For each block, hash value is computed, and then the hash value is the next block, and the old hash value, they are used to compute the next hash value. So MD5 as well as SHA-1 are considered too short, and Hans Doberteam from German BSI found a collision in particular in a partial function, in compressed function, so attackers are able to produce collisions and to, in this way, to break these hash functions. So please do no longer use MD5 in your application because you are not sure. Same is true for SHA-1. I already mentioned SHA-1. It is the secure SHA-1 secure hash algorithm. It was also developed in 1991 by NSA. Also is based on the hash function MD4. And then in 95 there was a revised version, SHA-1. Also SHA-1. Together with MD5 is one of the most common cryptographic hash functions in the internet. It processes 512-bit blocks like ND4 and generates 160-bit hash values. So to give an example, when we apply the hash function SHA-1 to the text a friend drives all over Bavaria in an utterly suburban taxi, then the SHA-1 100-bit hash value has this style in the format of hexadecimal description. When we speak about security, then also SHA-1 is no longer considered secure. And there are proofs also the hash value is 160-bit, so it's no more considered secure. And the first messages from the weakness of SHA-1 came from February 2005, where a Chinese team finds another, only theoretical possible is this attack, another way to crack SHA-1 with 2 to the 69 attempts instead attempts. This was improved in August 2005, this attack. So there was possible to produce a collision in 2 to the 63 attempts. And then in February 2017, last year, Google researchers demonstrated first a SHA-1 hash collision. So they proved and showed that it's possible to produce a collision. That means to produce two documents with the same hash value. They required 2 to the 60.3 SHA-1 operations. It needs 110 high-end graphic cards working in parallel for approximately 1 year, but then they found the collision. And this shows that also SHA-1, although it's very popular, is no more considered secure. So the recommendation from the NIST now is that users should make a transition from SHA-1 to the saver hash functions. There is the SHA-2 family. This was standardized 10 years later than SHA-1 and MD5. It was standardized between 2002 and 2004. It is usable and applicable for different hash lengths. So this shows that SHA-2 to 4 produce hash values of length 224. So it's much longer than the 160 from SHA-1. There is a version SHA-256, SHA-384, SHA-512, so that if the computers become stronger and the attacks can be performed also for larger hash lengths, there is a possibility to prolong the hash length. There are some minor weaknesses known, but this is more for a theoretical application. We have the SHA-3, which is standardized in October 2012. It provides alternatives procedures to SHA-2, and today this is classified as safe.